Hi, my name is Nels Newman. Our paper titled Generative RGB-D Face Completion for Head-Mounted Display Removal presents several findings of my master's thesis research at TNO, which involved the exploration of a generative approach to the virtual removal of head-mounted displays in RGB-D images. This year, we attend this workshop from home. How incredible would it be if we could all be in the same space, yet in our own house? With the emergence of VR technology, we are honing in on a new era of communication. Virtual environments can be turned into shared virtual environments by assembling multiple people in the same space. An example of a system like this was created by TNO, where this research was carried out. Both users wear a head-mounted display, an HMD, through which they observe a shared virtual room where they are represented as a point cloud. This can be generated based on an RGB-D image recorded by an RGB-D sensor, marked in red in the top image. However, as can be seen in both images, there is an issue. Specifically, we can observe that the HMD worn by the subjects occludes the upper part of their face, which prevents a sensor from capturing it. And this forms a major barrier for communication, as it prevents observers from interpreting nonverbal information or to recognize the identity of others. Removing this obstruction is referred to as HMD removal. Several image-based approaches to this have been proposed. However, none consider RGB-D images, which are essential for the volumetric representation of users. The primary objective of this work is to resolve the occlusion by filling in the missing color and depth information in this RGB-D image. So given RGB-D face image I containing the masked region omega, the aim is to consistently fill in the region of omega, which is shaped like an HMD. We focus on realism and identity specifically, leaving factors such as audible and temporal correctness out of scope. Our framework is founded on the RGB image painting framework by Yu et al. It consists of a coarse-defined generator and a discriminator. During training, the objective of the generator is to accurately inpaint the input image, whereas the objective of the discriminator is to determine whether the inpainted image is real or not. A key challenge is the simultaneous completion of both the color image and the depth image. We solved this through a naive approach to fusion, which simply concatenates the color and depth image at network input, which feeds into the first stage of the generator. This stage then produces a coarse inpainted result. Following the work of Matthias et al., we estimate the surface normals based on the coarse depth image. The X, Y, and Z normal components are represented with RGB values in this case, giving us a good view of the surface represented by the depth image. This image is then fed to a contextual attention branch, which ensures that information from the known image regions are propagated to the masked image region. At the end of this stage, we obtain a refined, inpainted result, which is our completed face image. In turn, the discriminator evaluates the image patches in the different spatial locations and channels in the resulting RGB-D image, and decides whether they are fake or real. This results in the GAN loss value, which is part of the objective function, which guides the training process. Also part of this function is the reconstruction loss, which stimulates pixel-wise reconstruction. In addition, we employ the vectorial loss by Matthias et al., which measures the reconstruction error of the surface normals of the inpainted image and the ground truth image. And lastly, to preserve the identity of the subject, we employ an RGB-based identity loss, which minimizes the mean square distance between the identity embeddings of the reference RGB image and the inpainted RGB image. These embeddings are obtained by passing the respective images through a pre-trained face recognition model, for which we use ResNet 50 trained on VGG Phase 2. In absence of a sufficiently sized RGB-D face dataset for training and evaluation, we built a pipeline for the creation of a synthetic dataset. This pipeline is based on the Basel face model, which is a parametric model that is built based on the facial scans of 200 different people. This parametric model allows the exact control of the shape, texture, and expression of the face, allowing us to create thousands and thousands of faces with unique identities. After sampling from the parameter space of the model, we obtain a 3D mesh of a face. On this mesh, we position an HMD based on a set key point between the eyes. As such, the HMD is appropriately positioned and has the right size. Lastly, based on the composite mesh containing the face and the HMD, we render an RGB-D face through a simple ray tracing algorithm. This gives us an RGB-D image of the face and of the mask. To explore the effects of each of the discussed components, we can compare the outputs of models that have been trained with different configurations. Firstly, we observe that the model trained with our identity loss, model C, produces identity features that are consistent with the provided reference image. Moreover, we observe an improved symmetry of facial features. Interestingly, while the identity loss is calculated based on the RGB channels alone, the depth channel of the inpainted images also show corresponding facial features. This indicates that the model learns the relation between the identity loss and the depth image indirectly, based on the feedback it receives regarding the inpainted RGB channels. As a consequence of the addition of the vectorial loss, we can see a clear improvement of the smoothness of the inpainted depth image and its surface normal representation. However, we do spot some inconsistent connections to the known image region. A possible explanation is that this flaw has a limited impact on the value of the vectorial loss function. And lastly, the model that was trained with the contextual surface attention module does not show a significant visual improvement right away. So let's take a look at what the quantitative results tell us. Firstly, we can identify a clear and significant improvement as a consequence of the identity loss, as we see an improved result across all metrics. Also similar to our observation during our visual examination are the results of the vectorial loss. However, it seems like the improvement comes at a minor cost, which is a decreased quality of inpainted RGB channels. Lastly, comparing the results of method E, we observe that the addition of surface information to the contextual attention module improves the objective metric results. And this suggests that the addition of the surface normal information may have improved the similar patch search procedure of this model. In this paper, we proposed a GAN-based framework that is capable of simultaneously filling in the missing color and depth information of RGB-D face images occluded by an HMD, while preserving identity. Source code of our framework is available online. While we explored more complex forms of fusion, our framework uses data-level fusion. To improve the feature construction process and ultimately the results, we recommend further exploration of multimodal feature fusion. Also, more research is needed to explore the other subtasks that image-based HMD removal comprises, such as eye gaze reproduction, temporal correctness, and audible correctness. To evaluate the framework, we devised a pipeline for the creation of a synthetic dataset. And while this allowed us to accurately control the recording conditions, our pipeline creates pixel-perfect images. RGB-D sensors often produce images with noise and misalignments, of which a simulation could be further explored. Alternatively, the model could be fine-tuned with real-world data. Despite its limitations, our exploratory research has made several contributions that will likely be of interest to future research on multimodal image painting methods and approaches to HMD removal. Thank you very much for listening.